Okay, I thought I'd go ahead and do a video exploring this because I've always wondered what would happen, if this diode didn't exist or whatever. And so basically, what I did is I, built a new regulator, a 317 regulator circuit there, and I basically got a bunch of um, resistors here. I got like 440 ohms, two half-watt resistors in series, um, you know, acting for R3 here. Okay, and I got two diodes in series, but right now they're disconnected, but I'll connect them up in a while. And I got my resistor box for our R2 here, and then for the 75 ohm I actually used a 120 ohm resistor, so which is typical. And I did go ahead and put the capacitor in just to see what happens. But I got this thing powered by, like I typically do, plus or minus 16 volts. And right now, you can see where I've got it set at in the analog discovery, or C1, is at 4.7 volts. So, so that's basically where we're sitting at the moment. I got my decade box set, like you see there, as a load for the moment. Well, not as a load, but as a program, because this is set up as a program current, so it's the potentiometer. Then I do have my big, potentiometer set at 100 ohms, because that's its max, connected as a load, because I'm going to demonstrate something that I was suspecting, and that this is kind of proving it. So again, I got no diode. I have two diodes in series, just small signal diodes, but I disconnected one of them. So, but basically, what I'll do is, I'll set the camera here, and you can see the blue trace is, I don't have anything going into it, but that's your zero reference, and the yellow trace is our, our voltage output. And I don't know if you can see on the other side there, but it's, 5 volts. You can see the scale here. It's right around 5 volts, and then 10 volts is the next step up, etc. So, if I increase this up too far, it'll trip my power supply. Turn it up a little bit. Let's see. But we're at 80 milliamps right now on the positive supply. Now we're at 120 on the positive supply, so that's 10 volts, 120 milliamps. But now I'll start decreasing it, and again, there's no diodes in there, but our negative reference terminal, is at minus 16 volts. So, we're getting closer. Let me up it like that. Now we're down below, it's minus 1.25 volts. Now we're down to 1.3 volts, and our current is about, 10 milliamps, and it's a little higher on the negative terminal now, about 30 or pushing 40 milliamps. And, this is with all resistors turned off, so it's just strictly the, it's just strictly those, that 440 ohms I have for R3, and then the 120 I have across the adjustment terminal and the output. So that's all the resistance there, but we're generating minus 2.3 volts. Now watch what happens. Now our current level on the positive side is 10 milliamps, on the negative side it's 40 milliamps now. I think it was 20 earlier. Now watch what happens when I start to increase the current here. We're up to current still holding the same on the power supply, but I'm reducing the resistance. In fact, we're almost down to 0. In fact, now we're at 0. So I've got basically a short circuit on the output to ground, because that's what this potentiometer is connected across as ground. So what you see here is, like I said, these regulators cannot sink current. They can only source it. what's sinking the current, okay, is our feedback resistors. And that's why you see the voltage rising as I diminish the load resistance, because that's the only place the current can actually go. That and maybe if any kind of protection diodes are in there or something like that, but I'm not aware of any. But at any rate, that's where current will go in this, because it can't source current. I can't sink current, can only source it. So what happens is, as the current starts to increase, through R1 or tries to, well, it makes the regulator think its voltage is too high. So what does it do? It dials back its output. So that's what's basically happening in response. To me, lowering the load towards ground is that it's actually dialing back its output to compensate. So, that's why you're seeing the voltage actually rise towards ground, but really its output is actually diminishing, because it can't sink current, it can only source it. So, and it's our load, drawing current from ground through our reference resistors that's increasing the voltage across the reference resistors that's making all this happen. So in practice, even if you didn't have those diodes, you'd have a hard time sinking too much current into it. But normally you wouldn't want that to happen. So, you would like put diodes in it, like I'm about to reconnect this other diode. Okay, that's what happens. Nothing. And that's with a short circuit to ground. But now our current's dropped up on the negative terminal at the 50 milliamps. Now let me dial the load back to 100 ohms. Okay, so now I got it at 100 ohms again, and you probably can't see that, but our voltage is actually a quarter of a volt below ground. And again, I tried it with one diode, but it ended up being about a half a volt above ground, so that's why I decided to put two into it. But I just wanted to demonstrate, what kind of happens, in this process, and, what's sort of involved in it. Now I'm going to start turning up our, again, because I had all my, programming resistors set to 0, but now, we've got a positive voltage across it, 300 millivolts, 61 millivolts. So, so basically that shows you what happens, when you break the rule. And like I said, remember right now I got diodes in it. So if I turn again all of our reference resistors off, C1 is still about minus 40 millivolts with a 100 ohm load. And even with no load, a short circuit, it's still pretty much the same, 40 millivolts. So, so basically, oh, well, I did have 20 ohms turned on, I'm sorry. So yeah, so there's our quarter volt back. So even at zero resistance, we're at 22 millivolts positive, and as I turn down, as I turn, because I just shorted the load again, but as I turn the load up back up to 100 ohms, quarter of a volt, So anyway, that shows you kind of what happens with the thing. And oh, by the way, as a bit of unfinished business, I did look into this, and as far as more into the theory, and again, I still can't find any real good descriptions of it, but there is no fucking way. Basically this is meant for a center tap transformer. So the center tap is your return. So you can think of 3 taps, with your upper tap, your voltage tap, and your lower voltage tap of the transformer going here, and then the center ground coming out and acting as a return. And these 2 terminals, with the transformer terminals being hooked here, act as your new transformer terminals. So that's just the only fucking way this thing works, because again, as I just demonstrated, these things cannot sink current. They just neglected to put that fact on here, and I haven't found any data sheet that really explains it, even though there's newer data sheets out that at least say something about their demo circuits, but they still didn't explain that. But that's how this thing's meant to be used. So it's kind of interesting. But if you were to use it, like I said, because again, it can act to reduce ripple current in your power supply. But remember, you might need some TBSs or something in there, and definitely some MOVs or something on the primary in between your switch and your transformer. because again, those transformers will generate high voltages when you turn them off if you hit them at the wrong time. And there's a good chance you're going to hit them at the wrong time, and that will create a surge. Normally you have filter caps that catch that and absorb it. But here there's no filter caps. This is on the AC side, right? So, don't run these too high, because these are never meant, like here, they're never meant to be more than about 6 volts away from each other. That's why it's a 6-volt clipper, because like I said, when this is at, well, okay, this is a 24-volt version. If you look at the 317 data sheet, it has a 12-volt slash 6-volt version, because this is really set for 6 volts, unless this has just got different properties to it as a regulator, but they use the same exact resistor values in the 317 version, and their diagram is 12 slash 24. If you do the math, I mean, it makes sense that that should be a 6-volt output, assuming this is 1.25 volt. So, that's why it's clipping at 6 volts, because it'll, in this case, it shows 12, but the 317 it should be 6. Because these two regulators will never be any more than about 6 volts from each other on the output. So that's why it clips, because of that, because this signal is the signal in this terminal is 180 degrees out of phase with the signal in this terminal, so it's 24 volts max in this case, but it's clipped to this, again assuming these are 2.5 volt reference instead of 1.25 volt. That's the only way you get that, but that's how it works. And but you could put TVS's in here somewhere on these inputs that kind of deal with that a little bit, but these two still would be 24 volts apart from each other, but there could be a maximum of 40. So if you put a 30 volt TVS or some bidirectional TVS in there, you might be able to catch some some transients, and you can definitely put them with respect to the center terminals, and they don't have to be as extreme. So that might be one way of kind of protecting these, but again, that might make you for a little bit quieter of a power supply, because you're not dealing with extreme currents through the rectifiers and everything, of your bridge rectifier or what have you, and your ripple currents are going to be lower, so it's going to be easier in your capacitor, and lowering peak currents is always a good idea. If you're trying to look for a peak, a quieter power supply, this is something you might research. So, so anyway, I just wanted to pretty much cover that, and give you that update on these two things, and so that ought to do it. Cheers. By the way, if I didn't say it, cheers.